Welcome back to the Deep Dive, where we unpack complex ideas so you don't have to. Today, we're embarking on an architectural journey into the essential, and maybe sometimes terrifying, demands of mobile systems.
It's a fascinating area.
It really is. And our source material lays out the blueprint for this field, which is, well, kind of amazing when you consider how fast it all evolved. Think about Alexander Graham Bell's famous early prediction. The telephone will be used to inform people that a telegram has been sent.
Right, just a notification device?
Exactly. He saw it as merely, a little alert system. That really underscores how completely unexpected the ubiquitous and frankly complex nature of modern mobile systems turned out to be.
It does highlight a staggering architectural failure of imagination back then, but one we've certainly course-corrected on pretty quickly.
Definitely.
And when we talk about mobile systems and software architecture today, we're not just talking about the smartphone in your pocket or purse.
Right. It's broader than that.
Much broader. We are discussing any device think trains, planes, satellites, robotic systems, industrial sensors out in the field, basically any device that lacks a permanent, continuous connection to an abundant power source.
Okay. So our mission today is to distill the core challenges from Chapter 18 of Software Architecture and Practice. This chapter outlines 5 critical characteristics that, well, fundamentally differentiate designing these mobile systems from, say, designing fixed server systems.
It's really an exploration of continuous compromise, isn't it?
That's a perfect way to put it, continuous compromise.
Yeah, these 5 characteristics force trade-offs at pretty much every stage. First, there's the fundamental constraint of energy.
To the big one.
Definitely. Second, the chaos of network connectivity.
Always fun.
Third, the integration of sensors and actuators, how the system interacts with the real world.
Okay.
Fourth, the tight physical budget of resources weight, size, cost.
Right.
And finally, the specialized life cycle requirements, especially around things like testing and deployment. They're just different.
Let's dive into that first one then, the most constrained boundary, energy. Whether you're running on a little lithium-ion battery or a massive fuel tank in a plane, the supply is limited.
And every single calculation, every bit transmitted costs something. Energy, money, battery life.
So what's the architect's job here? What are the main worries?
Well, it boils down to maybe 3 big headaches. First, how do we actually monitor the finite power source accurately?
Okay.
Second, how do we conserve power, throttle things back when the supply gets low?
Makes sense.
And third, how do we make sure the system stays intact, keeps its integrity when the power fails entirely, which it eventually might?
Right. So monitoring sounds like more than just that percentage number we see on our phone screen.
Oh, much more. Under the hood, we're talking about the smart battery, which incorporates something called a battery management system, or BMS.
BMS.
Think of the BMS as the battery's own internal accountant. There's usually a kernel component in the OS that constantly queries the system to track remaining capacity, sure, but maybe more critically, it monitors how the battery itself is aging.
Aging. How so?
Its current maximum capacity, which degrades over time, and the maximum sustained current it can reliably provide. Batteries aren't static.
Ah, okay.
So if the system knows these characteristics are deteriorating, it can do useful things. Warn the user, sure, but also trigger a battery-saving mode automatically, and crucially, notify running applications that a shutdown is imminent.
So they can wrap up gracefully?
Exactly. Save their state, finish critical operations.
That real-time data then allows the system to actively conserve energy. The source material calls this throttle usage. What does that actually look like? What's the trade-off?
Throttling is all about intentional degradation. It's a necessary evil sometimes.
Right.
The most visible trade-off is often the display. You reduce the brightness, maybe lower the screen's refresh rate.
Which you notice immediately.
You do. It impacts user experience, the feeling of responsiveness. On the processing side, we might reduce the number of active processor cores or just decrease the clock rate.
Slower performance, but longer life.
Precisely. Sacrificing that instantaneous speed for longevity. For sensors, maybe a GPS location check goes from happening every few seconds to only once a minute.
Big difference.
Huge. The trade-off is always balancing power conservation against the quality, the timeliness, the accuracy of whatever service the system is providing.
Okay, and then the third headache, the power failure itself. If you're designing for energy scarcity, you have to plan for the moment it just runs out.
Absolutely. Resilience here isn't optional, it's mandatory. Systems need graceful tolerance and, importantly, robust restarts.
How robust?
Well, for high criticality systems, there's often a strict requirement, Like, after power is restored, the system must return to its nominal working mode within a very short window, maybe 30 seconds.
Wow, 30 seconds from zero.
Yeah. And the implication for the software architecture is massive. The runtime environment has to be designed so that if it's just abruptly killed power cut, the integrity of permanent storage is unaffected.
So all the programs, the configurations, the user data.
All safe, untouched. Furthermore, the system has to ensure state consistency when it restarts, meaning it must either resume exactly where it left off.
Or do a predictable clean reset.
Exactly. No corruption, no weird states.
That sounds like a huge challenge, just dealing with that one physical constraint, energy. But if managing the power you have is tough, what about dealing with a communication link that keeps, well, dropping off? Let's talk network connectivity.
Yes. The challenge here is just the sheer variety of ways to communicate wirelessly, coupled with the fact that the device is usually moving. It's inherently unstable.
Right.
Architects are dealing with networks basically categorized by distance. You've got the really short-range stuff like near-field communication, NFC, maybe 4 centimeters.
Like capping your phone to pay.
Exactly. Then Bluetooth or Zigbee, maybe 10 meters. Wi-Fi gives you perhaps 100 meters. Then you jump up to WiMAX for several kilometers. And then there's the long haul, cellular and satellite covering vast distances.
With all those options and new ones popping up, there must be a huge temptation to just include every possible radio, cover all the bases.
Oh, absolutely. But that temptation must be aggressively resisted. This is what the chapter calls interface minimalism.
Why minimal?
Because you aren't just adding software complexity when you add a protocol. You're adding physical components, chipsets, antennas.
Which take up space.
Space, generate heat, and maybe worst of all, drain the battery even when they're sitting idle, just being powered on costs energy. So minimalism is really key for optimizing power, heat, and physical size. Only include what's strictly needed.
Okay, so you choose your interfaces carefully.
Yeah.
But then the system has to actually use them intelligently as the device moves around, right?
Yes, exactly. The design has to handle seamless movement. Imagine you're streaming, say, a big video file over your home Wi-Fi because it's cheap.
Right.
Then you walk outside, the Wi-Fi signal drops. The system needs to switch over to the maybe more expensive cellular network without your stream stuttering or failing. The user shouldn't even notice.
Tricky.
Very. And if multiple networks are available simultaneously, maybe you're in a spot with both Wi-Fi and good cell signal, the system needs to engage in dynamic protocol choice.
Meaning it picks the best one.
It intelligently picks the best one based on a careful balance of factors. Things like cost, sure, but also available bandwidth and the device's current power consumption. Maybe it prefers Wi-Fi if the battery is low, even if cellular is faster.
Okay, and what if there's just no network, like driving through a tunnel?
Yeah, the architecture has to anticipate intermittent and limited connectivity. Data integrity is absolutely paramount here.
You can't lose data.
You can't. So degraded modes or fallback modes have to be available dynamically. Computation might need to pause and then reliably resume without losing state consistency once the signal comes back.
And security must be a bigger issue, too.
Huge issue. These devices face heightened security vulnerabilities because they're often connecting to untrusted networks, public Wi-Fi, for instance. Makes them easier targets for attacks like spoofing, eavesdropping, man in the middle, you name it.
Okay, moving from the digital network realm to the physical world around the device, let's explore sensors and actuators. How do we turn physical reality into usable data and vice versa?
Right. So first, quick definitions. A sensor detects something physical in the environment, temperature, light, motion, acceleration, and converts it into an electronic signal the system can understand.
Like a thermometer sending a voltage reading.
Exactly. And an actuator does the reverse. It takes a digital command from the system and performs a physical action. Think activating a car's braking system or moving a robotic arm.
Got it. And managing all this input-output.
It can be a huge data load, especially with many sensors, so architects often use a sensor hub. This is basically a specialized little coprocessor. Its job is to gather and maybe do some initial processing or integration of sensor data, offloading the main CPU.
Which saves battery again.
Precisely. Conserves that precious energy.
So the core architectural challenge here sounds like taking potentially masses of raw, maybe noisy data from all these different sensors and creating one single reliable picture of the environment.
That's it exactly. Think about identifying a pedestrian if you're a self-driving car. That takes input from cameras, maybe lidar, radar, all working together. This conversion and interpretation happens through what's called the sensor stack.
This sensor stack.
Yeah, it's like a confederation of device drivers and software layers that transforms those raw readings, maybe just voltages, into meaningful, actionable information.
What are the key steps in that stack? How does it work?
Well, it usually starts with reading raw data. The software
Yeah.
driver queries the sensor periodically, and the frequency you choose is a direct trade-off read. More often, you get more up-to-date info, but you use more processor power.
Okay. So you get the raw data.
Then, you usually need smoothing data. Raw sensor data can be noisy. Think voltage fluctuations, maybe grime on a camera lens. It can cause jitters. So we use techniques like moving averages or more sophisticated things like Kalman filters to reduce that noise and variation.
Kalman filters, what do they do, basically?
Think of a Kalman filter as like a sophisticated digital jitter reducer. It takes the current noisy sensor reading, compares it to a prediction of where the reading should be based on past readings and the system's model, and then it corrects the input. It sort of mathematically smooths things out, trusting its prediction slightly more than a single erratic reading.
Clever. Okay, smooth data. Then what?
Then converting data. Different sensors might report in different units, millivolts, feet, Celsius. You need to standardize these into a common, meaningful form the rest of the system can use. And finally, perhaps the most complex part,
Which is
sensor fusion. This is where you combine information from multiple different kinds of sensors. Maybe a thermal imager, radar, lidar, cameras, all looking at the same scene. The goal is to create a representation of the environment that's far more accurate, more robust, more dependable than any single sensor could ever provide on its own.
because each sensor has strengths and weaknesses.
Exactly. Fusion compensates for those weaknesses. Without it, complex tasks like reliable autonomous navigation are pretty much impossible. And of course, you also have to plan for failures here too, if the main sensor fails, like GPS in a tunnel.
You need a backup plan.
Right. The system has to switch to a degraded mode. Often uses dead reckoning, basically estimating your position based on your last known velocity and direction until the primary sensor comes back online.
Okay, that makes sense. Let's shift gears now and look at the resources section. This seems to be where we deal with the hard physical limitations: size, weight, heat, cost. This is where decisions get expensive and, well, pretty permanent.
Yeah, this is really the meeting point of engineering reality and commercial reality. The architect is constantly balancing a resource's capability, what it contributes to performance against its physical footprint.
Footprint meaning?
Volume, weight, the heat it generates, and crucially, its cost. Because remember, many mobile systems are manufactured by the millions. Smartphones, cars.
So they're incredibly price sensitive.
Intensely price sensitive. Even a few cents saved per unit adds up massively.
So constraints are coming from the customer, like market expectations.
Right. Marketing might dictate a certain size or a minimum display quality.
And also from just the laws of physics.
Correct. Physics imposes non-negotiable safety requirements, obviously. Weight limits are critical, especially for anything that flies or even drives efficiently. And thermal limits are huge. Heat generated by the system itself, or just high ambient temperatures where it operates, can be a primary cause of system degradation or outright failure. Things literally melt or shut down.
So in a big mobile system, like a modern car, which has dozens of processors, how does the architect manage allocating tasks within that physical and cost budget?
Right. In larger systems like cars or airplanes, the architecture dictates how tasks are assigned to electronic control units, or ECUs.
ECUs, like little specialized computers scattered around the vehicle.
Exactly. Think of them as distributed microbrains. Software subsystems get allocated to these ECUs based on several factors. Fit to function, maybe use specialized graphics processors for the display. Criticality safety functions like braking get dedicated, maybe redundant hardware. Physical location matters too. Sensors need to be near the ECU processing their data, connectivity needs, and always the overarching goal is minimizing the total number of ECUs to save cost and complexity.
Makes sense. Yeah, sometimes the processing needed is just too much for the device itself, right? We see work getting pushed elsewhere.
Absolutely. That's the common tactic of offloading to the cloud. Complex functions think calculating the absolute optimal navigation route in real time, considering traffic, or doing really sophisticated image or pattern recognition. These can be split.
How so?
The mobile device gathers the raw data, using its sensors, maybe does some pre-processing, then sends it off. The powerful cloud servers do the heavy computational lifting and send the result back.
What are the trade-offs there?
The architect has to constantly weigh the benefits access to massive processing power against the drawbacks. Is the network connection reliable enough? Is the latency, the round-trip time, acceptable? And increasingly, what are the privacy concerns about sending potentially sensitive operational data off the device?
Right, privacy is huge. We also see systems deliberately reducing functionality sometimes to free up resources.
Yes, shutting down functions. A great example is like a race mode in a performance sports car. When you activate it, the system might disable non-critical comfort functions. Maybe it stops doing fine-grained climate control calculations or shuts down parts of the infotainment system.
Why?
To free up every last bit of processing power and network bandwidth exclusively for the critical performance systems, managing torque distribution to the wheels, optimizing braking stability controls, adjusting suspension on the fly, it prioritizes.
Okay, one last resource mentioned is the display itself.
Right, the display strategy. The sheer resolution and size dictates how much information you can reasonably show. This often motivates architectural patterns like model view controller, MVC,
Why MVC?
because it separates the data model from the presentation view. This makes it much easier to swap out different views for different devices, a high-res tablet versus a small smartwatch display without having to rewrite the core logic.
Clever. Okay, finally, let's tackle the unique lifecycle challenges, particularly around testing and deployment, which the chapter stresses are fundamentally different from mobile systems.
They really are, and often the whole development process gets flipped on its head. For many mobile systems, especially embedded ones, hardware selection happens before the software design even starts.
The hardware is chosen first. That sounds problematic.
It's a major structural constraint. The software architect can't just passively accept these constraints. They need to be actively involved, driving those early hardware discussions, really emphasizing the painful software trade-offs that will result from maybe suboptimal or cost-cut hardware choices down the line.
Okay, assuming the hardware is chosen, what are the unique testing nightmares mobile systems introduce?
Oh, there are several special kinds of hellscapes here.
Chuckle slightly.
Okay. Display layouts are incredibly complex. Devices come in just a dizzying variety of shapes, screen sizes, aspect ratios. Simulators often just don't catch the nasty edge cases, like controls suddenly overlapping weirdly, or a button shrinking down to a tiny, unusable 1x1 pixel square in some odd corner configuration you didn't anticipate. You also have to test really specific operational edge cases, like does the system actually preserve its state correctly after the battery has been run completely flat and the device has been cold killed and then restarted? Simulating that perfectly is hard.
So simulators often don't quite cut it.
They often don't, especially for things like getting accurate battery consumption testing. You really need to test that on the actual physical hardware under realistic load conditions. And testing network transitions is incredibly difficult to get right in the lab.
Making sure it switches smoothly.
Yeah, ensuring the system switches seamlessly, say from Wi-Fi to cellular, or hops between different cellular towers as you move without the user noticing anything, and critically without any data getting lost or corrupted during that handover. That requires extensive field testing.
For really high-stakes systems like industrial controls or automotive, testing is obviously super rigorous. The chapter mentions 4 levels.
That's right. It's a structured approach. You typically start testing at the software component level, just testing individual pieces in isolation for basic stability.
Okay.
Then you move up to the function level. Here, related components run together, usually in a simulated environment, to validate that they interface correctly, that they work as a coherent feature.
Makes sense.
Third is the device level. Now you take that function software and deploy it onto the actual target ECU, the real hardware, but you might still use simulated inputs and outputs to test its performance and behavior in a controlled way on the real chip.
Right.
And finally, you get to the system level. This integrates all the different ECUs, all the devices, into the full configuration, the whole car, the whole plane, to ensure all the subsystems work together correctly in the final environment.
And traceability is key.
Absolutely crucial. A key requirement across all 4 levels is test traceability. If you find a bug way up at the final system-level integration test, you must be able to trace it back, reproduce it, and fix it down at the relevant component, function, or device level.
Okay, so testing is complex. Once a fix is verified, actually deploying updates brings its own set of issues, right?
Right.
Especially around safety.
Safety is paramount, yes. First, you have to determine which system states are actually safe for applying an update. You absolutely cannot, for example, update the engine control software while the vehicle is driving down the highway at 70 miles an hour.
Definitely not.
Updates are also often automatic, pushed out over the air, and frequently they're one-way, meaning there's no easy rollback path if something goes wrong. This really favors using cloud-based storage for historical data, configurations, etc., so you can potentially restore things if needed. Architects also have to plan for partial deployment and extendability, structuring the system using good modularity principles so that parts that change frequently, maybe user interface elements or map data, can be updated easily and independently without touching the core safety-critical systems. And you have to think about retrofitting. Long lifetime systems like trains or planes might be in service for decades. You need an architecture that allows for integrating newer technology years after the initial deployment.
And underlying all of this, to figure out what went wrong or how things are being used, is logging.
Logging becomes critically important, yes, both for incident resolution, figuring out why something crashed, and for usage analysis. But because a mobile system's location and network connectivity might be intermittent or even non-existent for long periods.
Like that research submersible example.
Exactly. Log data absolutely must be offloaded whenever possible to an accessible central location, like the cloud. It needs to happen opportunistically, whenever connectivity allows. This ensures that even if the device itself is currently inaccessible, maybe it's offline, maybe it's physically broken, you can eventually retrieve the logs you need to troubleshoot or analyze its behavior.
Wow. Okay, what a fantastic deep dive. We've covered the 5 indispensable architectural categories that really force continuous compromise in mobile systems. Managing the finite supply of energy.
The constant constraint.
Navigating that complex, often messy network connectivity.
The wireless world.
Interpreting the physical world via sensors and actuators.
Talking to reality.
Balancing those tight physical resource constraints, cost, size, heat.
The engineering versus commerce battle.
And finally, mastering the unique lifecycle challenges of hardware constraints, all that complex testing, and safe, reliable updates.
Yeah, those 5 characteristics really define the foundation of this entire field. They explain, at a deep level, why designing, say, a scalable app that runs on your phone is fundamentally different architecturally from designing the massive cloud server infrastructure that supports the phone app. Different worlds.
Absolutely. So, turning this back to you, our listener, we discussed tolerating a loss of power and that typical 30-second restart window requirement. But let's push that. If you were designing a highly critical mobile system today, maybe avionics software for an aircraft or a critical medical device, what specific architectural choices would you prioritize to ensure that a complete loss of power is tolerated gracefully and the system can seamlessly restart exactly where it left off without compromising any data integrity, including its operational state at the moment of failure?
That's a tough one. Lots of trade-offs there.
It is. Think about the trade-offs involved. Thank you for joining us on this exploration of software architecture.
Thanks, everyone.
We appreciate you being a part of our deep dive learning experience today.